Hello everyone, welcome back. In this particular video, we're going to start talking about reactions that happen at the alpha carbon. Specifically, we're going to talk about a halogenation at the alpha carbon. And this reaction is also called just a alpha-halogenation. And this reaction we're going to look at for carbonyl compounds. So this would include ketones and aldehydes. And when ketone or aldehyde, a carbonyl compound in general, is treated with a halogen under acidic conditions, then it can undergo the alpha-halogenation, okay? So they will undergo halogenation at the alpha position, which means the alpha carbon, under both acidic and basic conditions. We're going to start off by looking at the acidic conditions. How does this reaction proceed under acidic conditions? So examples, I've basically put a generalized example here and then some specific examples. So if we have a carbonyl compound, and again, I'm just using this generalized structure to represent either a ketone or an aldehyde. So if we have a carbonyl compound, it can react with halogen, and the halogen can be any halogen. So all halogens would work here, okay? So your X can be anything. So chlorine or iodine would also work. This reaction is not observed for fluorines though, so we would not be using fluorines here, but chlorine and iodine is fine. So when you react this carbonyl compound with a halogen under acidic conditions, you will get the alpha-halogenation, and that means the alpha carbon gets halogenated. And so notice for this compound, this is an alpha carbon. And if you keep track of hydrogens, this alpha carbon here has 3 hydrogens on it. Okay, there are 3 hydrogens here. So there are 3 alpha hydrogens for this molecule. And so essentially what we're doing is a substitution in some sense, because what we're doing is we're substituting one of these alpha hydrogens with a halogen, bromine specifically in this case. Okay, so that's the alpha carbon, and it has 2 alpha hydrogens on it now. One of them has been substituted with a Br, and we get HBr along with it. Some specific examples: acetaldehyde, you react it with Br2, and acetic acid is what I'm using here. So that would be the acid that is doing the reaction. In fact, acetic acid is also used as a solvent for some of these reactions. So acetic acid, and you get the alpha halogenation. So the alpha carbon here gets halogenated. Cyclohexanone with bromine and acetic acid, again, the alpha carbon gets halogenated. Now, for cyclohexanone, there are 2 sets of alpha carbons. So in principle, you can get a double halogenation, which means you can put halogen on the other side also if there is bromine available in excess. So you can do halogenation on both sides of that, on both alpha carbons here. Okay, but if you're looking at a stoichiometric reaction, then we're only going to put halogen on one of these alpha carbons. So again, the alpha carbon is what's getting halogenated under these conditions. Next, let's look at a mechanism of this reaction. Now, this reaction involves enols. As we learned earlier, a lot of this chemistry involves the formation of either enols or enolates, which serve as nucleophiles. Enols are formed under acidic conditions, and enolates are formed under basic conditions. So let's look at the mechanism of the reaction. So the mechanism of this reaction starts with the formation of an enol. And so the first step, what happens is your carbonyl compound, it gets protonated by the acid. So we have acid around. So you're going to protonate this oxygen, the carbonyl oxygen. So that gets protonated. There's a proton transfer here. Okay. Under equilibrium conditions, you're going to make the protonated carbonyl compound along with water that will be generated. And once we are here, as we saw in previously in case of like enol formation, this protonated carbonyl compound, it can do resonance. So we can draw a resonance form for this molecule where we have a positive charge here. So essentially, we're just trying to show resonance here. This is not a step. This is just a resonance form that we're drawing. And from here, the alpha hydrogen, one of the alpha hydrogens, and the key would be that there is at least one alpha hydrogen present here, okay? So one of these alpha hydrogens can be deprotonated under these conditions to give us the enol. So notice we make the enol here. So we've synthesized the enol, or we've generated the enol intermediate. Now this enol intermediate, as we said earlier, is a good nucleophile, and it is nucleophilic from the carbon atom. So what this enol intermediate can do is, now it can go ahead and attack the halogen. In this particular case, it is bromine, but it could be whatever halogen is there, it's going to attack. And whenever we use an enol, if we use this resonance form of the enol, the way we show attack is we use the lone pairs on the oxygen, bring them down to form a double bond with the carbon, and simultaneously the pi bond can go and attack the halogen, and the other halogen is lost. So this will bring us to the next intermediate where we have double bond OH, one lone pair positive charge, and Br. Plus there's going to be a bromide ion along with that. So the bromide ion is also formed. And then from here, we're really close. So we do one final proton transfer. So a molecule of water or another weak base that's in the system that can go ahead and deprotonate that. And it would give us the alpha-halogenated compound plus H3O plus. So the reaction or this process is catalytic in acid because you are regenerating the acid here. Okay, so that's the mechanism of an alpha-halogenation under acidic conditions. It involves the initial formation of an enol and then a nucleophilic attack by the enol on the halogen atom, and it gives us the alpha-halogenated compound. So the halogen is at the alpha carbon of that compound. Now, in case of an unsymmetrical carbonyl compound, this is when we have a carbonyl compound and we have two unique alpha carbons. So notice for this particular molecule, we have two alpha carbons. We have alpha here and we have an alpha prime over there. So there are two potential alpha carbons here. So in such cases, it is observed that when you do the alpha bromination or the alpha halogenation of these molecules, the major product is when the halogen lands at the more substituted alpha carbon. Okay, that's the major product, and the minor product is going to be the one where the halogen is the less substituted carbon. So notice how alpha is only secondary in nature with the alpha carbon, whereas the alpha prime carbon is tertiary in nature. So this is secondary, whereas the alpha prime is tertiary in nature. And so it turns out the major product is where the halogen ends up on the more substituted carbon, not on the less substituted carbon. Why would that be so? The answer for this lies in the mechanism. So when you work through a mechanism for the formation of both of these products, this carbonyl compound, okay, it will, in the mechanism, okay, so in the mechanism, and I'm not working through the entire mechanism here, but if you work through the mechanism for this, you're going to get to the enol. Okay, the enol is formed under these conditions, and the enol serves as a nucleophile. So we're going to make the enol either this one or you're going to have another enol, which is this one. So those are, either another enol, which could be that one. So those are two possibilities for the enol. And when you look at the enol, notice how there's a double bond, okay? An enol is basically an alkene and an alcohol. And so the more substituted enol, the more substituted enol is more stable thermodynamically, okay? It is more stable. And so because of that, what happens is the major product, the alpha-halogenation product, results from this enol. And when this enol undergoes an alpha-halogenation, it's going to give us the halogen at the more substituted carbon. So that basically explains why we get this difference. And that is true for all chemistry involving alpha carbons or enols and enolates. When there is a possibility for forming different enols or enolates, the more substituted enol or enolate is the more stable enol or enolate, and they will give you the major product in the reaction. Now, the alpha halogenation is also possible under basic conditions. And a general reaction scheme would look like this, where you have a carbonyl compound and you react it with a halogen under in presence of a base. So we have a carbonyl compound and you react it with a halogen in presence of a base. And again, I'm using the Br2 here, but it doesn't have to be bromine. You can do the same reaction with chlorine or iodine if possible. Okay, so it really depends on the choice of the halogen, the product that you get. But if you do this, again, what we would get is we would get halogenation at the alpha carbon. Okay. Now the bromination or the halogenation under basic conditions, it is more difficult to control. And in fact, you get multi-halogenation. Okay, it does not stop at the monohalogenated. So this is called the monohalogenated product. You've put one halogen. But under basic conditions, if there are additional alpha hydrogens present, then the halogenation continues. Okay, so it is difficult to stop at monohalogenation if additional alpha hydrogens are present. So if there are additional alpha hydrogens present, then this reaction is difficult to control at the monohalogenated product. And essentially what happens is the reaction continues. This monohalogenated product will react with more halogen and base to give you the dihalogenated product, or till the alpha hydrogens are all exhausted. So in this particular structure that we are looking at, we had two alpha hydrogens here. And so our product is going to be the alpha dihalogenated carbonyl compound. Okay, so this is a dihalogenated product. Now we'll look at more specifics of this reaction. But before that, let's look at the mechanism. How does this reaction work? And that would also help us understand why the dihalogenated product is so much feasible here. Why doesn't it stop at the monohalogenation? Now, since the halogenation here is going on under basic conditions, the mechanism would involve the formation of an enolate. But the first step here is going to be the formation of the enolate, And so essentially what we're going to do is we're going to use the carbonyl compound along with the base. So as we would do in the formation of an enolate, the base is going to come and deprotonate the alpha hydrogen. Okay, that's the alpha hydrogen. It's going to deprotonate. Those electrons go to that alpha carbon. So we will get the enolate here, negative charge alpha. And recognize that the enolate here, this is resonance stabilized. Okay, so the enolate is resonance stabilized. So we can draw the major resonance form here, which is going to be that. Okay, so we can draw the resonance stabilized form of this enolate. So that's the enolate. It is resonance stabilized, and so under acidic conditions, the enol served as the nucleophile, and under basic conditions, the enolate would serve as the nucleophile. And so from here, what happens is the enolate is going to react with the halogen. So again, the way we can show this electron push is that lone pair comes down from the oxygen to create the double bond, and the pi bond here goes and attacks the halogen, and the other halogen gets kicked out, such that our product is going to be carbonyl with a halogen and the methyl group connected to it. And at this point, realize that we still have another alpha hydrogen there. Now, this monohalogenation process has added a halogen to that alpha carbon. And what that does is it decreases the pKa of that alpha hydrogen, or it makes it more acidic. So that means the base can now react with this alpha-halogenated product, the mono-alpha-halogenated product, to give you another enolate. And that enolate is going to be the Br with the negative charge here. Now I'm going to skip drawing the resonance form here, but this enolate can react with another molecule of the bromine to do a double halogenation. That's such that our product is going to be the dihalogenated product along with Br minus. Okay, so that's how we get to the dihalogenated product, or that's how we get to the multi-halogenated product. We're going to look at a more specific example here where multi-halogenation is possible, but that gives us a very different product mixture. Okay, but the halogenation basically keeps occurring till you have used up all of your alpha hydrogens. All of them are used up here. And the reason why that happens is because once the first halogenation happens, then this alpha hydrogen is more acidic. So it is easy for the base to deprotonate. If it could deprotonate the alpha hydrogen in the first carbonyl compound, then the deprotonation of the second alpha hydrogen should be much more easier. And again, those steps, the deprotonation and the protonation steps, they are all reversible steps because those are acid-base equilibria. Now, in the specific case of methyl ketones, okay, the halogenation of methyl ketones, these are ketones where one of the R groups is a methyl group. The other R group could be whatever, but one of the R groups is a methyl group. What happens is in such ketones, when a methyl ketone undergoes the alpha halogenation under basic conditions. Now I'm using excess bromine over here because, like I said, the halogenation is really hard to control or stop at the monohalogenation. So you will keep halogenating till all the alpha hydrogens have been exhausted. And in case of a methyl ketone, you can see that there are 3 alpha hydrogens. So all three of those alpha hydrogens would be used up. They would all be exhausted. So when you take a methyl ketone and do an alpha halogenation under basic conditions, and if you follow this with an acidic workup, what you get is a carboxylic acid as your product. So essentially, if you look at it, you're losing this methyl group. That becomes the hydroxyl group there. So you replace this methyl group with a hydroxyl group, and your product is a carboxylic acid. And along with that, you make this molecule, which is bromofoam, CHBr3. Now, it is bromofoam if you're doing a bromination. If you do a chlorination, then it will be chloroform, CHCl3 instead. Or it could be iodoform if you do an iodination instead. Now, these molecules, the bromoform and the iodoform, these have a very characteristic color, like yellow, orangish color to them. And so these molecules, or this reaction was actually used as a test for the presence of methyl ketone group earlier. Traditionally, we could do that because if you take a molecule and if you know if it's a ketone, and if you want to verify if it is a methyl ketone or not, what you can do is you can react it with bromine or iodine in excess, and then do this reaction in presence of a base. And if you see the formation of a yellow precipitate or an orangish precipitate, that would imply that your ketone was a methyl ketone. Okay, so you could use it as a test, a qualitative test for identifying whether your compound had a methyl ketone group in it. Okay, now I've got an example of here where we have acetophenone. So notice the R group here is a benzene or a phenyl ring, and then we have the methyl group. So when you do the halogenation on it using bromination, excess bromine and base, you get benzoic acid. The CH3 here is replaced by a hydroxyl group, benzoic acid, and you get the bromoform product here. Let's look at the mechanism of this reaction. How does it result in this loss of this methyl group? How do we lose it, and how do we get the bromoform? Let's look at the mechanism of this reaction. So what happens in the mechanism here is that you basically proceed by doing a halogenation. I'm not going to work through like an entire mechanism here, but I will show you some steps, and then we will fast forward in the middle, and then we'll get to the product. So if I start with this molecule, the methyl ketone, and I'm going to draw this hydrogen out, one of the alpha hydrogens out, for the purposes of our mechanism. So the first step is going to be the deprotonation of this alpha hydrogen by the base. The base is going to deprotonate it, and that's going to give us the enolate. Okay, it's going to give us the enolate here. And as always, this enolate is resonance stabilized. And again, it's not important to show this resonance every time. You can just use the negative charge on this carbon, the alpha carbon, and proceed with the attack. Okay, but this is the major resonance form because that lands the negative charge on the oxygen compared to the other resonance form where the negative charge is on the carbon atoms. That is the major resonance form. Okay, so the enolate, and now the enolate is going to react with bromine. And again, the way we show this attack is the lone pair comes down, and the double bond from here goes and attacks the bromine, and the other bromine gets kicked out as a bromide, so that we will get the mono-brominated product along with bromide. And since this mono-brominated product has two additional alpha hydrogens, you can imagine that this process is going to repeat itself twice more, two additional times. This is going to happen. So we're going to skip over that. So finally, after you work through the mechanism where you use each one of these alpha hydrogens one by one, and you work through a similar mechanism, you're going to arrive at a product like this, where all three of the hydrogens in this alpha carbon, okay, in the methyl ketone, they have been replaced by the halogen. So we should get to this tri-halogenated product. Okay, now once you get to this tri-halogenated product, since you have the alpha carbon with three halogens connected to it, now here the base, now this is where another reaction comes in. Now this is a reaction that we've seen before, and that reaction occurs under similar conditions. And in fact, this reaction that I'm going to talk about here, it is competing with this enol formation that's going on here. Okay, once you get to this intermediate here, there are no additional alpha hydrogens left in your structure. And your hydroxide is not just a base, it is also a nucleophile. So what the hydroxide can do is it can go and attack the alpha carbon, because the alpha carbon is electrophilic. So you can get an electrophile nucleophile reaction, and it would bring us to the next intermediate, where we have O minus, we have a hydroxide here, and we have the CBr3. Okay, so we've made a tetrahedral intermediate. Basically, this is a tetrahedral intermediate. Now this tetrahedral intermediate, it can collapse or it can add a proton. Either one is possible, but this tetrahedral intermediate collapses. And as it collapses, the CBr3 is kicked out. That serves as a leaving group because you have three bromines connected to that carbon. So that makes that carbon a good leaving group. So that's one example where a carbon-containing group is actually acting as a leaving group. And that's because there are three halogens connected to it. So the oxygen comes down and the carbon-containing group is kicked out here. And that would bring us to a carboxylic acid. Here we get the carboxylic acid, plus you're going to get CBr3 minus. And now, because we have a carbon-based nucleophile or a base here, a carbanion here, and we have a carboxylic acid, what this is going to do is it will deprotonate the carboxylic acid such that we finally end with a carboxylate plus CHBr3. So that's how we get the bromoform. And until now, we are under basic conditions. And so when you have this product set, which is the carboxylate along with the bromoform, and then you do the acidification, what happens is the carboxylate gets protonated to give you the carboxylic acid. The bromoform remains the bromoform. So that's the mechanism of how a methyl ketone is converted into a carboxylic acid when you do the reaction with the halogen. Now, this reaction in general, because you make the bromoform or the chloroform or the iodoform, this reaction in general is called the haloform reaction. So the reaction of methyl ketones with halogens under basic conditions is called the haloform reaction, like a chloroform, bromoform, or an iodoform reaction. So that's the reaction of methyl ketones and the mechanism of how the haloform product is formed, or how the methyl ketone is converted into a carboxylic acid under these conditions. In this part of the video, we're going to look at an interesting application of the synthesis of these alpha-halogenated carbonyl compounds. What we saw earlier is that a carbonyl compound can be alpha-halogenated under acidic conditions. And the alpha halogenation under acidic conditions is important because it will give us the monohalogenated product. It will give us the monohalogenated product. Now, why would we want to do this? One interesting application or reaction that you can do with this monohalogenated product is to react it with pyridine or a base, if you react it with a base. And the most common base that's used here is pyridine. We've seen pyridine earlier for other reactions. And what happens is when you do this reaction, you can convert this alpha halogenated product. Okay, so this is the alpha monohalogenated product into an alpha beta unsaturated carbonyl. It can be converted into an alpha beta unsaturated carbonyl compound. So there's a double bond between the alpha and the beta carbons. And alpha beta unsaturated compounds are really useful in organic synthesis. We're going to learn another method of synthesizing alpha beta unsaturated carbonyl compounds in the next set of videos. That's the aldol condensation reaction. But the alpha halogenation offers another method of synthesizing the same class of compounds. And this reaction here is basically an elimination, because when you look at it, you have the alpha halogenated compound. And if this is alpha, there are beta hydrogens here. These are both beta hydrogens. And so when you react this with a base, and pyridine being the specific example here, when you react it with a base, the pyridine nitrogen here is basic. So what that does is it will go ahead and deprotonate one of these beta hydrogens. And when that happens, the electrons between the beta, in the bond between the beta carbon and the beta hydrogen, they fall into the space between alpha and beta, and simultaneously the halogen is lost. So that would give us the alpha beta unsaturated carbonyl compound along with pyridinium. So since this is a base, this accepts a proton, so that's protonated now, and it would also have the bromide along with it. So that's how we get this alpha beta unsaturated carbonyl compound. So that's a cool application of these alpha halogenated carbonyl compounds. Next, let us look at two quick examples of using alpha halogenation under acidic and basic conditions. The first example I have here is a ketone, and we're reacting it with bromine under acidic conditions first, and then reacting it with pyridine, the product from there with pyridine. So if we look at it, what's going to happen is under acidic conditions using bromine, so this is the first reaction, our product is going to be, let's see what's our product going to be here. So we have two alpha positions, alpha and alpha prime. And notice how alpha prime is the more substituted position. So the halogen is going to go to alpha prime. So we'll get a bromine over here. That's where the bromine would end up. And then when we react it with pyridine in the second step, we are going to get an alpha beta unsaturated carbonyl compound. And in this particular case, that's alpha, and we have beta and beta. So there are two beta positions, but they're both identical. They are not unique. So our product here is going to be C double bond O, the double bond like that, where we have a double bond between the alpha and the beta carbons. So that will be our final product here. The second example is one of halogenation under basic conditions, but we've actually gone back a little bit. So we have an alcohol, secondary alcohol, and we're doing an oxidation on it. So this alcohol, when we do the oxidation on it with PCC, it should give us the ketone. And now we do the bromination on this with excess bromine in presence of a base. So when we do that bromination, this is going to convert this into the carboxylate ion. So because this is a methyl ketone, this bromination is going to convert the methyl ketone into a carboxylate plus bromoform. And then the final step is the acid workup or an acidification or protonation. And so what's going to happen is our carboxylate will convert into the carboxylic acid, and we would still have bromoform. So those are two quick examples of how this reaction can be used. Now, we used a methyl ketone here. That's why the bromoform reaction happened. If it were not a methyl ketone, we will just get a monohalogenated or a dihalogenated product, depending on the number of alpha hydrogens that are available. And somehow notice that to make the reaction less complicated, we are avoiding alpha hydrogens on one of the carbons. So there are two alpha carbons here, but one of them does not have any alpha hydrogens, because if we have alpha hydrogens on both sides, then we're going to get bromination on both of those carbons. Next, we're going to look at the alpha halogenation of a carboxylic acid. This reaction is called the Helmholtz-Zielinski reaction, and it starts with a carboxylic acid and does halogenation to convert it into an alpha-halogenated carboxylic acid. Now, the reaction is done in two steps. The first step is the reaction of the carboxylic acid with bromine and PBr3. And we'll look at the details of why this is needed, and followed by a hydrolysis, an acidic hydrolysis to get the alpha-halogenated carboxylic acid product. So let's look at the process here, what is going on here. And we're not going to work through a complete mechanism here, but rather go through the skeleton of what's happening in the reaction here. So what happens in this reaction is when you have this combination of bromine with the PBr3, what the phosphorus tribromide is doing here is it first converts your carboxylic acid into an acyl bromide. So this is basically similar to the acyl halide or the acyl chloride that we've seen before. So it converts the carboxylic acid into an acyl bromide, and then this acyl bromide, under our reaction conditions, it can basically form an enol of the acyl bromide. Okay, it will give us an enol of the acyl bromide. The acyl bromide can be converted into the enol form of it. So we have the acyl bromide here, and we have the enol form of it. And this enol form is what's reacting with the Br2. And very similar to how we've seen previously in terms of mechanisms. Actually, I'm going to call this steps instead of mechanisms because I'm not showing any electron push mechanisms here. These are rather steps in the reaction. So the enol now reacts with Br2, and it will give us the alpha-halogenated acyl bromide. And then finally, when you do the acidic hydrolysis, what that does is it converts the acyl bromide, which is a very reactive compound, into the carboxylic acid. So You first convert the carboxylic acid into the acyl bromide so that you can do the alpha halogenation. And then when you're done with the alpha halogenation, you hydrolyze the acyl bromide back to the carboxylic acid. And then this should essentially give you HBr also as a byproduct. So that's the Hell-Vollert-Zelinsky reaction. I'll not be going into further details here, but it allows us to convert the carboxylic acid into the into the alpha halogenated carboxylic acid. I hope you find these alpha halogenation reactions helpful.